is Dr. Diaz. Let's talk about light. The nature of light has been a subject of inquiry since antiquity. We start with Isaac Newton in the 17th century, for example, when white light consists of the individual colors of the rainbow combined together. Light was composed of streams of extremely tiny particles traveling at a high speed according to Newton's laws of motion. But Thomas Young in 19th century came up with a theory like light passing through narrow closely spaced light produce interference pattern, but it could not be explained in terms of Newtonian particles, but it could easily explain in terms of wave. So electrons are incredibly small. A single speck of dust has more electrons than the number of people who have ever lived on Earth. Electron behavior determines much of the behavior of atoms. As quantum mechanics developed, it was found that electron and light have many characteristics in common. Wave-particle duality. Remember that Newton was explaining based on a particle because the light behaved like a particle, but then sometimes like also behave as wave. So this is why we call wave-particle duality. Electromagnetic radiation can be used to interfere the energy of electrons with atoms and molecules. Electromagnetic radiation is the energy transmitted by waves that have an electric and a magnetic field component. So a wave is an oscillation or periodic movement. Let me grab a pen over here. That can transport energy from one point in space to another. Let's go to these images over here. Look at this. And the first over here, I will call the first one over here. That's the first. As you can see a man shaking the end of the rope, transferring energy from the athlete point to the other point of the rope. Here we have a drop of water. That's my second picture over here. That causes a ripple effect outward the water surface. The wave of sound of thunder over here. You can see a lightning over here, so we can hear the sound of the thunder. So we can see it here from far away, right? And each of this case over here, kinetic energy is transferred through matter, right? And in this first case over here, the matter here is the rope. And the second, the matter is the water. And the third one, the matter is the air. However, the matter remains essentially in place, right? What you see, we're not restricted to travel through matter. Maxwell is another scientist that showed that the wave can also travel through space. So wave, as I said before, is an oscillation or periodic movement that can transport energy from one point in a space to another. And is composed by two main fields over here. Electrical field component, they are both perpendicular over here, and the magnetic field component. So we have the electrical field, which is the electrical charged particle experience force, and the magnetic field, that is magnetic field, is a region where a magnetized particle experience a force. So light can travel through matter and through space, and travels at a constant speed through a vacuum. The speed of light is 2.998 times 10 to the 8 meters per second. You will need to memorize that. Please don't memorize 3.00 times 10 power 8 meters per second, okay? It's 2.998 times 10 power 8 meters per second. So light is a form of electromagnetic radiation. As I said, composed of perpendicular oscillation waves, one for the electrical field and one for the magnetic field. And thanks to electromagnetic spectrum, which is the range of all types of electromagnetic radiation, we can see those beautiful pictures that you can see over there. You can see the test tubes with different colors of solution, the green grass over there with the beautiful white little ball, And we have the orange, white orange color of the fire over there. So visible light makes up only a small portion of the electromagnetic spectrum because it has a very large range of magnetic spectrum. The total energy is proportional to the amplitude and the frequency. The larger the amplitude, the more force it has. The more frequently the waves strike, the more total force there is. This is the electromagnetic spectrum over here. So we have a very large range of spectrum, electromagnetic spectrum. We have the radio. So radio, we know, capture waves and radiates it to you, so you can hear AM, FM, TV, right? You also already use microwave, right, to warm your food really fast. So microwave is also used to study structure nearby galaxies. And we have also the infrared. Do you know where the infrared is used? So it's a type of electromagnetic radiation and invisible for us, but it's also used in infrared telescopes, for example. What else? So night vision goggles, right? And we have this very short part that is a visible line, which also is a good range of wavelength over here, right? And we have ultraviolet, and we also heard a lot of bad things about UV in our skin, right? But also it's used for what? Can you give me an example where ultraviolet is used, right? Remember when you go to the lab and they ask you to wait for the goggles because they're clean up? We're using UV, right? Why using UV radiation? To killing bacteria, creating fluorescent effects, or creating inks and resins. A lot of you use it. There in that case, we use to kill bacteria, right? And we also have X-ray. If you have been in the dentist the last days, probably they took X-rays of your teeth just to see if you have inflammation or cavities or something, right? And we have gamma rays. Gamma rays is the smallest wavelength that we have, and if you go to a doctor, they have to see you inside, or like inside of your body, they're gonna use gamma rays. And let's look at this. So what is a wavelength? Can you tell me that? So wavelength is the distance of the peak. Let me get a pen over here. So it's the distance of the peak between two consecutive peaks, right? Over here. Like I have over here, the distance between those two peaks. And the unit is meter. So, and the symbol is the lambda. Look into those two pictures. Can you tell me which one we can call A and B, or left and right? Can you tell me which one has the largest wavelength? Yes, left. You can see over here, right? We have a large wavelength and distance over here. And the frequency. What is frequency? So frequency is the number of peaks or successive wavelengths that pass a given point in a unit time. See what it's saying? Number of successive wavelengths that pass a given point in a unit time. So the unit is per second. And we also use hertz. The symbol is nu. Can you tell, look into those pictures, which one has the highest frequency? Left or right? Right is the right one because we have a short wavelength over there. Important to talk to you to say that we use common multiples of the hertz, and which the megahertz and the gigahertz. So it's really important to know how to use the units, how to use it as a unit factor, like a giga, we know is 10 power 9, mega is 10 power 6. It's really important. So after these two exercises that we did over here, like which one has the largest wavelength and which one has the highest frequency, you could see that when you have a large wavelength, we have a small frequency, right? So they're inversely proportional. So the relation between those wavelength and frequency is this. When one is large, the other one is small. So we can relate to that in a formula. So the speed of the light, which is c over here, is the product of the wavelength and the frequency. Again, the speed of light is 2.9979 times 10 power 8 meters per second. Just to highlight this again, wavelength and frequency are inversely proportional. As the wavelength increase, the frequency decrease, and vice versa. And here we have a good examples over here. So see here the distance traveled in 1 second. Look at this, how many cycles per second we have. See here, I only have 1, 2, 3 on this, while here I have 1, 2, 3, 4, 5, 6 cycles, so 6 hertz per second. And while here I have 12 because I have a smaller wavelength, okay, per second. I think this is a very good example to understand, okay. I think this is it. That's all.